Alright, so welcome guys to the next episode. In today's video, we're going to be discussing about kinematics. Now, kinematics in general seems like a heavy topic, but when we go deeper, right, when we try and understand each one of these topics in greater depth, we understand that each one of them are just basically interlinked, right? And they're basically the same. Because when we talk about two-dimensional kinematics, which is basically a projectile motion, it's basically two one-dimensional kinematics acting in different axes. And we'll also notice more such interlinking and similarities in the topic, throughout physics, not just in kinematics. So let's just go ahead and wrap up kinematics. Let's finish it, let's crush it. And this might be a 1 hour session or maybe a 2 hour session. So make yourself comfortable, get in the environment, and let's go ahead and begin. Now, hopefully there's no error in this shooting, because shooting 1 hour 2 hour videos, yeah, that that actually takes a lot. So hopefully everything goes as planned, and let's go ahead and begin. Also, I bought a new graphics tablet, so hopefully my handwriting is better from last time. And if you guys haven't checked out the vectors video that I had shot earlier, which is already uploaded on the channel, make sure you guys do that. And now let's go ahead and begin. So we're going to go ahead and begin with the term motion and rest itself, right? So first let's understand what exactly motion is and what exactly rest is. Now, from younger grades, you would have heard that rest and motion are relative terms, right? What exactly does the statement mean? What does it mean that rest and motion are relative terms, right? What can we infer from this? So, what it really means is that a body, right? Let's say this box A. This box can either be in motion or at rest, depending on the frame of reference. For example, you would better understand this with a car. So let's say we have a red car. All right, let's say we have this red car, and hopefully I can draw car well, because if I don't, then I should probably go back to preschool. So yeah, so this is our red car, and let's say just parallel to it, or maybe just further away. Hopefully you guys understand that this is um, 3 dimensions, so it's behind it, right? It's basically parallel to this. Now, if I say that this red car over here is moving with a velocity of 20 kilometer per hour, right? And let's say this over here, this green car is basically moving with the same velocity, 20 kilometers per hour. Now, I guess you would have noticed that when you're on a highway, right? When you're on a highway and when you're speeding your car at, let's say, 100 kilometers per hour, 120 kilometers per hour, more than that, it's kind of unsafe. But let's say you're speeding at 100 or 120 kilometers per hour, right? So, do you see other cars flying past you at 120 kilometers per hour? Not really, unless they're over speeding and going at 200 kilometers per hour, but not really. Why does this happen? This is the concept of relative motion. This is what we are going to be understanding, right? Now, relative motion can be a little confusing in the beginning, right? It might be a little confusing, but as you go deeper into kinematics, you will get a great understanding of this. Now, a better example of this, I mean, the most common example, I'm pretty sure if you go to any teacher, ask them to teach kinematics, they will give you this example. So let's say you're in a train. All right, this is a train. Don't judge my drawing. This is a train. And yeah, let's say this is a train. Now, this train is moving forwards. And here, there's a man who's standing outside. And here, there's a man who is within the train. Now, let's say you're sitting within the train, right? Do you see the train moving away from you at, let's say this train is moving at 50 kilometers per hour? Let's say you're sitting at your seat. Do you see that the train is moving away from you at 50 kilometers per hour? Not really. You feel as if this entire thing, the entire scenario within this train is at rest. Everything is at rest. But when you look outside, when you look at the trees and everything, then you would notice that the trees are moving behind, right? They're going away from you. And they are moving, actually, if you, as we proceed, you will realize that these trees will seem to move at 50 kilometers an hour in the opposite direction, right? So now let's talk about this guy, right? Now, from his perspective, from his vision, okay, that's vision, that's not laser shooting out of his eyes, that's his vision. So what he would be seeing is that this entire train, along with this person, is moving forward with a velocity of 50 kilometers an hour, right? That's what he would be noticing. But now we seem to have a problem. Which one of them is actually lying? Who is right over here? So what physicists came to say was that no one's right, no one's wrong. What happens over here is you have to basically look at the frame of reference, right? You have to look at the frame of reference. For this guy sitting within the train, the frame of reference was the train, right? Was everything inside the train. He saw that those things were at rest. And when he looked outside, he saw that the ground was moving backwards. He saw that the trees were moving backwards and everything was moving backwards other than the train itself. Right? Now, similarly, when we talk about this guy over here, his frame of reference was the ground. He could see that the ground is at rest. Alright, he saw that the ground around him was at rest. But the train over here was moving forwards. This is the concept of relative velocity. This is why we say that rest and motion are relative terms. Right? This is why it makes sense. Because with one person's perspective, an object can be at rest, but with the perspective of another person, the object can be in motion. Another great example for this is that, okay, let me just go ahead and try changing this. Okay, I'll convert this to yellow. And let's choose this. Okay, we already have red. Which one would be good? Nah. Let's say brown. Okay, that didn't work. Let's say brown. Alright. So now let's talk about our solar system. Alright. Now I know it wouldn't make sense, but let me just go ahead and explain this to you. So now we have Mercury, Venus, and Earth. Alright, I'm gonna draw this blue planet right over here. Yeah, that looks more like Neptune, but sure. Let's say that's Earth. Now, you might be sitting on your table and chair. You might be sitting on your chair, or you might be on your bed, or you might be on your sofa. You might be sitting or standing. Do you see that the Earth is moving? Do you see that ground is moving? You don't, right? But let's say there's an alien. Alright, let's say there's this UFO who is just creepily staring right at you while you're sleeping. Right? So, according to this person, according to this alien, what he sees is that you are on Earth. And the Earth is moving. Therefore, you are moving. Right? So, that is what he concludes. But for you, you're not moving. The Earth is not moving. For him, you are moving as well as the Earth is moving. So this is why your rest and motion are relative terms. You just have to look at the frame of reference. You have to see what from what perspective you're looking at, right? Hopefully you got a good hold of it, right? Now we are going to be talking about one dimension, two dimension, three dimension. Now, what exactly is dimension? Right, what exactly is dimension? So when we talk about one dimension, when we talk about 1D, that's basically a line. Alright, just one line. It's just a straight line that looks like this. Alright, so if there's motion happening in a straight line, that is known as one-dimensional motion. Then we have something called as 2D motion. Now this is actually a plane. So this motion takes place on a plane, right? So let's say this is a plane that we have, right? And let's say this is an ant. Let's say this is an ant. Now let's say this ant moves here, there, here, there. So you can see that this involves two axes, right? It involves two axes. What are the two axes? It's up to you how you want to, give its nomenclature. Most people call this y-axis. Most people call this x-axis. Right. That looks like alpha. I'll make it x. So you can see that over here, only one axis is involved, right? You can see only the x-axis is involved. But over here, you can see that the x and the y-axis is involved. And over here, this is basically just a straight line, while this is an entire plane, right? So the motion is happening on the plane. Now, when we talk about three-dimensional motion, okay, let's talk about three-dimensional motion. Also, if you guys are wondering why I don't have my webcam on, no, it's not that I'm insecure about the way I look. It's basically I'm trying to figure this out. What's happening is the frame rate is dropping and the webcam is actually looking really crappy. So until I figure that out, hopefully I can do that in the next 2 to 3 upcoming episodes, and then that would make us more comfortable. If you're able to see the person who's teaching you, that's a lot more comfortable than just listening to him. But hopefully you guys can manage it just for these 2 to 3 lectures, and then we'll basically see, right? Then we'll basically figure it out. I'll try figuring it out. Now, what is three dimensions, right? What is three dimensions? In three dimensions, it's basically you have three axes involved, right? You noticed y, you noticed x. Now where does the third axis go? The third axis goes in the plane of your screen, all right, and comes out of the plane of your screen. We call this the z-axis, right? So now this is a line, this is a plane, and this is I don't remember what exactly you call this. See, this is line, this is a plane, and yeah, let's just call this 3D, whatever. This is just 3D. So yeah, so far we have discussed about rest and motion being relative terms, and also what 1D, 2D, and 3D motions basically mean, right? Now when we talk about frame of reference, I think I explained that to you earlier. Frame of reference is basically the scene, right? When we talk about frame of reference, that is basically the scene, okay? It's the scene used to judge motion. Okay, frame of reference is basically the scene that is used to judge the motion. Like for example, if we move up to our old case over here, come on. Okay, how did I do that? That was that was pretty cool. Okay, anyways, so when we come back over here, we notice that this guy over here, right, the person was inside the train. This guy over here, I can actually use a highlighter too. So this guy over here, yep, what? Okay, fine. So this guy over here, for him, the frame of reference was the train, and for him, the frame of reference was the ground. Its frame of reference is basically what stays at rest when a person compares two scenarios, right? So for this guy standing outside, the ground remains at rest, while for this guy, the train remains at rest. So whatever remains at rest, that becomes a frame of reference, because you're judging whether motion is happening with that into perspective, right? With that perspective, with keeping that in mind, right? Now, I can really not go more detailed than that. Now we're going to be moving to terms associated to motion. So first we talk about distance. Distance, I talked about this a lot in vectors. So distance is basically the path length covered between any 2 points. Let's say you want to go from your home to your girlfriend's home, right? So you can directly go from your home to your girlfriend's home, or you could choose another route. Or let's say you want to be creative. Here's the sun. Let's say you go towards the sun, you burn, you turn hot, and now you go back to your girlfriend, right? So the distance is basically the total path length, right? Distance is the total path length. Distance is it's the total path length that is covered by an object moving from one point to another, right? Then we talk about the next term, which is displacement. So distance can be of infinite varieties, right? You can have infinite ways to go from one point to another, right? There are infinite ways. But when we talk about displacement, there's only one displacement. Displacement is basically the shortest path length between any 2 points. And the shortest path between any 2 points is basically the straight line joining the 2 points. So if I have to go ahead and write what displacement is, it is basically the shortest path length, shortest path length, which is basically a straight line. Hopefully you guys like my handwriting. Shortest path length, or which is basically a straight line between any 2 points, right? Between 2 points. So there can be infinite distances, but there can be only one displacement. And another difference is that a displacement is actually a vector quantity, while your distance, I'm pretty sure you guys figured it out, your distance is actually a scalar quantity. So now we looked at the differences between displacement and distance. There might be more there might be more differences, but here what we are trying to do is trying to understand what physics really is from its base, and not just feed information to ourselves and cram it, because that's not the right way to actually learn it, right? Even physics is a skill and we need to master it stepwise. So there's no point of me just telling you the differences unless they don't really make sense to you. So that's what I'm trying to do. So I'm trying to take in everything and teach it to you once I'm sure that you guys can understand it, right? So now we are going to be talking about, okay, let me just scroll down. Now we're going to be talking about speed. Speed is basically the rate of change of distance, rate of change of distance with respect to time. With respect to time, right? So make sure that you I'll just increase the thickness if there's any way to do that. Yeah, there should be a way to do that. Okay, okay, I got it. Okay, so keep this in mind, distance, right? You need to keep that in mind. Distance is the important word over here, and similarly when we talk about velocity, right? When we talk about velocity, that is basically the rate of change of displacement, right? Over here the important word is displacement with respect to, again, what? Time, right? So we basically look at how much distance has been covered in how much interval of time. So I'll basically give you the formula as well. So here displacement is the important word, and there we go. Now let's go ahead and write a few differences. Let me just put this in the corner. So if we go ahead and talk about a few differences, first of all, this is a scalar quantity and this is a vector quantity. This is scalar, this is vector, right? And if we go ahead and talk about the formula, we can just write speed is equal to distance covered upon time taken. All right. And if we talk about velocity, we can write velocity is equal to displacement covered, there can be only one displacement, so upon time taken. So if you guys want an example of how do you solve a question, so let me just give you an example question. So let's say we have an example question. Let's say we have 2 points, right? We have point A and B. We know that the straight line joining those two is of the length, let's say 500 kilometers, right? Now let's say I go from point A to B, I travel a route like this and I come over here, right? Now, the entire path length of this route is actually 1200 kilometers. Now, let's say it took me, the time that is given to me is 10 hours, right? It took me 10 hours to do this journey. It took me 10 hours to move from A to B. Now, can you tell me the velocity and speed? Um, you can go ahead and pause it and give it a try while I explain it to you. So hopefully you guys have given it a try. Even if you haven't, no problem. Let's go ahead and see how we solve this question. So first, let's find the speed. Speed is basically what? Speed is basically the total path length, which is 1200 kilometers, by the time taken. Time taken is 10 hours. So it's going to be 1200 upon 10. So we get 120 kilometers an hour, right? But when we talk about velocity over here, when we talk about velocity, that's going to be the displacement covered, right? That's going to be the displacement covered. Displacement is basically 500, time is again 10. So here it's going to be 50 kilometers an hour. All right. So this is how we do a basic question over here, right? Just to give you an example of how you can use these two terms. Now we have multiple different types of, we have different types of speed and velocity. All right. So first I'll just go ahead and tell these terms to you. All right. So that you get familiar with it. So first we have uniform. All right. Uniform speed or speed slash velocity. All right. So uniform speed slash velocity. So what exactly is uniform speed or uniform velocity? Uniform speed and uniform velocity means that the speed slash velocity remains constant. By constant basically means that it does not change, right? So let's say I'm going from my house, all right, let's say apartment A to apartment B. Let's say I'm over here. So what uniform speed slash velocity means that if I'm traveling with 10 kilometers per hour initially, then till the point I reach my destination, which is point B, I should still be traveling with 10 kilometers per hour with the same velocity that I started off with at every single point. Now, then we can say that the journey between the points A and B was, done with uniform velocity or uniform speed, right? So that is what uniform velocity and uniform speed means. Now, when we talk about non-uniform velocity slash speed, right, it's basically the opposite, right? At least at one point or maybe at more points, the velocity can actually change. It can be variable. So here this is constant and here it can be variable speed slash velocity. Now we have the most important, right? Now comes instantaneous, right? Now comes instantaneous speed slash velocity. So instantaneous speed slash velocity basically means the speed or velocity of a body at any instant of time, right? At any instant of time, the velocity or the speed of the body is known as instantaneous speed slash velocity, right? That is basically, the word itself says. So now when we talk about this, how exactly do we find instantaneous speed or velocity of an object? So basically over here, one of the prerequisites will be basic differentiation, right? Basic differentiation and integration. Basic differentiation and integration, right? So if you guys don't know it, so you can currently just skip it, right? You can skip this and I'll just write it as prerequisite. Okay. Now, um, if you guys don't know this, right, if you don't know how to differentiate or integrate right now, no big issue. I'm going to take a session on that as well. I was planning to take that next before I teach Newton's laws of motion and work power energy. So you guys can cover it over there and then come back to this particular point. For those of you who know basic differentiation and integration, what instantaneous speed or velocity means is that your, let's say your distance slash displacement over here. Let's say distance, let's say we take distance as s, no, actually let's take distance as um okay, what should we take, z, and let's take displacement, as s. Now, what your instantaneous speed, so if you write speed instantaneous is equal to, this is majorly the notation that I'm going to be using throughout this course. So when I write speed instantaneous, it basically means instantaneous speed. And I'm going to speak it out so you guys will figure it out yourselves. So when we talk about instantaneous speed, it is basically the differentiation of the distance with respect to time, right? When you differentiate this with respect to time, then you get the instantaneous speed at that particular point. When you differentiate distance with respect to time, then you get the instantaneous speed at that particular point. Similarly, for velocity, let's say we are talking about velocity instantaneous, you have ds by dt, right? Which basically means that when you differentiate displacement with respect to time, you get instantaneous velocity at that point, right? So yes, I really can't see how long it has been since I started shooting this. So I don't know when I should be giving a break, but right now let's continue. Once I feel a little, once I feel that the information that I've given is good enough, it's worth taking a break, then we'll go ahead and take a break and you guys can chill out and I'll just chill out too, and then we'll begin again, right? So let's go ahead, and there's another way to write this actually. I just saw it in the reference and I just remembered. So if you want to write this in another way, we can write this velocity, right? We know that velocity is basically delta s upon delta t. Delta s means the change in displacement divided by the change in time. Alright, that is our velocity. This velocity is known as average velocity. Alright, when you do this. But when we talk about instantaneous velocity, when we talk about v instantaneous, then what happens is you have the same thing, right? You have the exact same thing, but there's one slight change. Limit delta t tends to 0, delta s upon delta t. Now, this is understandable for those who have done a little bit of calculus themselves. But if I have to explain this, there's a simple way to understand this. So let's say we're looking at a graph, right? Just give me a second. Let's say we're looking at a graph, something like this. Let's say I'm plotting displacement along this and time along this, right? And let's say I'm getting the graph something like this. Okay, something like this. This is my graph, right? Now, what average velocity basically means is, let's say I want to find the average velocity between these 2 points, right? Average velocity doesn't exactly give me a precise value of velocity at any particular point. Average velocity just tells me that if I were to travel at a constant speed for that given time interval, what would, no, actually, I'm really sorry, I framed it wrong. What I meant to say is to travel the same distance but at uniform velocity in the same time interval that it took over here. That uniform velocity is basically known as the average velocity. I'm going to repeat it again. Let's say I have to travel this, let's say this entire distance that it has traveled is x. All right, let's say the displacement is x, right? So if I have to travel x distance or displacement in time interval, let's say the time interval over here was delta t1, right? If I have to travel x displacement in delta t1 time interval, then what would be the uniform velocity that it would take me to do so? That uniform velocity is known as the average velocity. Now let's say we want the instantaneous velocity, right? So for instantaneous velocity, what we go ahead and do is okay, no, that's not how you do it. I'm still learning how to use this thing properly, and hopefully I don't make a joke out of myself. This eraser should have been bigger. This is just okay. Okay. Oh, oh wow. Wow. Okay. So what I was saying was, so earlier we looked at a huge time interval. Now let's say I want to know the velocity of the body at this point, exactly this point. So what we do is, let's say initially in the previous case we were looking at something like this, right? Just give me a second. We were looking at the average velocity between this time period, right? Between this time interval. So what we begin to do is we begin to move this, we begin to shift it towards each other, right? We shift it such that in the next interval they'll come closer. Again, they're going to come closer. So we're basically reducing the time interval. Initially we took this as a time interval, then we reduced it to this much, then we reduced it to this much, but we actually want a really small time interval, and we go ahead and find the average velocity for that really small time interval. Let's say I'm finding the average velocity of the body for a time interval of 0.00001 second, right? What is the average velocity of the body between the for a time interval of 0.001 seconds? So if you see, this quantity is very small, right? This quantity is very small. So basically what it means is that the average velocity over here would actually be the net velocity of the object. Do you understand what I'm trying to say here? What I'm trying to say is basically that if the time interval is extremely small, right, if it's almost zero, then the average velocity basically becomes the velocity of the body at that instant of time. That is why this delta t, okay, it's lagging a little, I'm really sorry. So what this over here signifies, let me just show you what this over here signifies, that the time interval that we are taking, it's slowly tending to zero, right? So initially, let's say we took delta t equal to 10 seconds, then we took delta t equal to 5 seconds, then we took delta t equal to 1 second, then we took delta t equal to 0.00001 second, right? And then we took delta t equal to 0.0000001 second. So basically when we are reaching a point where it's almost equal to zero, when it's tending to zero, then at that particular point the average velocity becomes the instantaneous velocity, and that is what we have signified over here. So instantaneous velocity you can write in two ways. Let me show you both the ways. I'll just write it over here. So you can write v instantaneous, okay, so you can write v instantaneous as either ds by dt, or you can write that as limit, give me a second, limit delta t tends to 0 delta s by delta t. So this is basically your average velocity for a very small time period. This is differentiating it with respect to time. Okay, cool. We got it. Right, now we will be moving on to, let's see. Yeah. So now we'll be moving on to relative velocity, right? Before that, I'll just have a quick sip of water, and you guys can have too. So now we have come to a point of kinematics that most of the people find confusing. Now we have come to relative motion. Alright, now we have come to relative motion. Now, in relative motion, there are quite a few shortcuts that if you apply and if you think a little logically, it just saves the day for you. And if you go stepwise, it actually makes it kind of complicated. To get a better feeling of relative motion, let's try understanding this. Let's say there's a ball. All right. Imagine that you're inside this ball, or imagine this is a car. I can't keep drawing a car over and over again because that takes me quite a while and it's pathetic. You get it. So let's say this ball is traveling at 5 kilometers an hour. And let's say in front of it there is another ball, right? And that is traveling at 2 kilometers an hour, right? So of course we know that if this is a one-dimensional motion, this ball over here will just go ahead and strike it at some point, right? At some point it would hit this ball because this over here has a higher speed because we know 5 is greater than 2. So this over here has a higher speed than this over here, right? So we know that this ball that's following up, let's say ball A will go ahead and crash into ball B. Now, if I ask you, what is the velocity? Let's say you're sitting inside this. Let's say you're sitting inside this car. All right, let's say that's a car. That's a ball car. It's 20. It's 3050. Right? We have ball cars now. So let's say you're inside a ball car, right? And you're seeing this car that's moving in front of you. So could you tell me what the velocity of this car B over here would seem like to you? That that if you answered 3 kilometers, that's absolutely right. Now could you tell me the direction in which this would seem to come? Now imagine yourself in this scenario if you're not able to find the answer, right? Just imagine yourself. Let's say you're driving on the highway and there's a truck in front of you. Trucks go pretty slow, man. They're annoying, especially on a highway. Let's say that is going at 20 kilometers an hour. And let's say there's only one lane. Let's say it's not a highway, it's just some road. And you are coming with 50 kilometers an hour in a car, right? So this truck would seem to you that it is moving with a velocity of 30 kilometer an hour away from you? No, towards you. It's moving 30 kilometers per hour towards you because you're catching up to him. Right? Do you understand what I mean over here? You are catching up to him. Okay? So now, I'll just go ahead and tell you a quick shortcut that would allow you to solve any kind of question, right? So let's just take an example of a question. Let's say that there are, first let's start with something simple. Let's say there are two cars. All right, let's say this is car A and let's say this is car B. All right, first you tell me something. Let's say this is moving with 50 kilometers an hour and let's say this is moving with 20 kilometers an hour. Do you think that this car A would ever be able to hit car B? Not really, right? It won't unless that car B brakes. And yeah, so it won't. Now, let's say we are supposed to, now I'm going to go ahead and use the terms, right? I'm going to go ahead and use the terms with respect to you a lot. So let's say we have to find the velocity, find velocity of B with respect to velocity of A. All right, how do we go ahead and do this? How do we do this, right? Let me just give you a quick shortcut. So let's say you have these two cars. Just go ahead and draw them again. You don't have to exactly draw a car, just draw two boxes. So we know this is traveling at 50 kilometers an hour and this is traveling at 20 kilometers an hour. Now this velocity of B with respect to A is also written as, if you want to know the nomenclature, we read VAB. All right, this is what? This is, just give me a second. This is velocity of B with respect to A. All right, velocity of B with respect to A. And similarly, if I gave you, let's say, velocity VBA, so could you tell me what this would be? This would be velocity of A with respect to B. Now, let me just go ahead and give you another example. V12, can you tell me what this would be? This would be velocity of 2 with respect to 1. Cool. And one last example, let's say V43, what would this be? This will be velocity of 3 with respect to 4. All right. So whatever is in front, right? Give me a second while this is not clicking. Okay. Whatever is in front over here, that comes over here. And whatever is behind this, that comes right over here. Now, we need to find velocity of B with respect to A. Right, we need to find velocity of B with respect to A. So can we write that as VBA? So this is what we have to calculate. Right, velocity of B with respect to A. So let's go ahead and do this. The shortcut over here is, first of all, let me just go ahead and tell you the formula as well. If you have to find velocity of B with respect to A, that is basically VB minus VA. This is the formula, but I would never suggest you to use the formula. The way I'm going to teach you is based on intuition, and you can never go wrong by that. Over here, formula, the negative sign can be a little confusing, and especially we know that velocity is a vector and it matters a lot. The sign really matters a lot. But over here, if we use logic, that's going to help us better, right? So velocity, okay, I'm really sorry. We wrote this wrong. We wrote this wrong. I'm really sorry. You guys might have figured it out. So this actually should be VAB. Just give me a second. Yeah. So this is going to be VAB. AB. Now whatever comes towards the end comes before the negative sign, it's basically positive, and whatever was before that, this A over here, that will come with a negative sign. Now if you want to use the formula, you can. It takes like 2 seconds, but I'm not going to suggest you that. We will go ahead and figure this out using intuition. Now what we are going to do is we're going to go ahead and find, let me just move over here, and let's draw these two again. I know this might be a little frustrating, but it's definitely worth it. Right, so this is moving with velocity 20 kilometers an hour, while this over here is moving with a velocity 50 kilometers an hour. All right, so what basically is going to happen, let's say this is A, this is B. So we need to find velocity. I know I'm saying this for the billionth time already, but this needs to fit in your mind, because the first time I tried to do velocity, relative velocity, I really couldn't grip on the concept. So once you actually grip on this relative velocity concept, everything is kind of simple, because after this relative velocity, we only have 2 more topics. One is going to be a projectile motion, which is super simple, and also your 3 equations of motion, that's like super important, and also your circular motion. I might keep circular motion for Newton's laws of motion, because over there you'll get a better understanding of what tension really is and what centripetal forces are, pseudo forces. So it wouldn't really make sense right now. We'll see about that, right? So now if you want to use the formula, you can directly do it. You'll directly get the answer. But now what does this mean? This VAB means velocity of B with respect to A. So what we do over here is we need to find this with respect to A, right? So with respect to A, what does that mean? We are taking A as the frame of reference. And what did I say initially about the frame of reference? Frame of reference is something around you that is at rest, using which you can judge motion. Like let's say you're sitting on your chair, right? And then a bottle flies past you, right? So how will you judge whether that bottle is in motion or not? You're going to look at your chair, or you're going to look at your surrounding. They're at rest. So your surrounding basically becomes your frame of reference while your bottle is in motion. So what it says over here is with respect to A. With respect to A, that basically means that we need to take A as the frame of reference. That means A has to be at rest. Now, to make A at rest, what do we have to do? Let's go ahead and look at that. So I'm going to draw it again, and I know it's annoying, but we have to. That's how physics is done. So this is at 20 kilometers an hour. This is at 50 kilometers an hour, right? This is 20, this is 50 kilometers an hour. Now we need to make A at rest. So basically we sit in over here, and now we want A to be at rest. You know what we can do? What we can do, and you might have never heard of it, is give everything over here a velocity of 20 kilometers per hour backward. Now, why did I do 20 kilometers per hour backward? See, so we know that A over here is moving with a velocity 20 kilometers per hour in the forward direction. If I want to stop this, how much velocity would I have to give to A, and in what direction, so that its net velocity becomes zero? Because I want it to be the frame of reference, and the frame of reference has zero velocity, right? So what I do over here is give A the velocity of 20 kilometers an hour in the opposite direction, right? In this direction, I will be giving A the velocity, right? And then it comes at rest. Now, if I'm giving A 20 kilometers per hour in this direction, then I need to give B 20 kilometers per hour in this direction too. So what do we get over here? What does our final scenario look like? Let's go ahead and see. So if we look at it, if this is our A, now this has come to rest, right? Now this is at 0 kilometers an hour. And if we look at B over here, B is actually moving, it's still moving forward. Why? Because 50 minus 20. Why did we do minus 20? Because it is in the opposite direction, right? Do you understand what I'm trying to say over here? So it would seem, if you're sitting in A, it would seem as if the bus B or car B is moving with a velocity 30 kilometers an hour away from you, in front of you, right, to the right. Okay, so now if we have to finally give the answer, VAB will be equal to plus 30 kilometers an hour, assuming positive is towards the right. All right, the sign convention is up to you. All right, you can choose whatever direction you want as positive and whatever direction you want as negative. That is completely up to you. All right, so that is what relative motion basically is. Now let's look at another question, and this question we're going to do a lot faster because now we understood the concept. So let's say that again we have two cars. This is car A and this is car B. This time what we are doing is we're going to do car A moves with 10 kilometers an hour towards the right, while car B moves 30 kilometers an hour towards the left. Now I need to find VBA. Actually, we'll give the vector sign as well, so that would, let us know that we want the direction as well. If the negative sign is there, we'll know that. Okay, so before that, let's just define the convention. Every single time you start a problem, you can define a convention. I always take right as positive because why not? And yeah. So now it really doesn't matter if you take left as positive, your negative sign would basically display that it is moving in the right direction, and if you're taking right as positive, then your negative sign would be meaning that your body is moving in the left, right, in the opposite direction basically. So if you guys are having any confusion with these vector signs and all of that, you guys can just go ahead and see the previous video on vectors and watch it on 2x, 1.5x. It's on how fast you can learn, how fast you can grasp the knowledge. And it's no problem even if you're watching at 1x, not a big deal. Um, so yeah, so now we need to find VBA vector, right? So how do we do this? Again, what does VBA mean? It means velocity of B. Okay, I'm really sorry. I keep making this mistake over and over again, and I realized it this time too. Let me just, okay. So VAB, all right, VAB. So VAB means that velocity of B with respect to A. All right, VAB means velocity of B with respect to A. Now again, if we take a closer look, what are we looking at from what frame of reference? From A, right? Again, what we're gonna do is, let's say we're gonna what I will do is I will learn how to copy and paste. Okay, this time I'm actually gonna try learn how to how do I copy. Oh, what? Oh, okay, no. Oh, that's that's kind of fancy, but okay. How do I? Okay, I'm trying to zoom in, and is it going to zoom in? No idea. Yeah, it. Okay, it's okay. Coming closer to 100% zoom. Come on, come on. Okay, 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 and perfect. Right. So no, it's not worth it. It's not worth the try. Okay, let's just scroll down, scroll down. Where were we? We were over here. Right, let's just draw this diagram again. It's really not it's not worth it. So what we have over here is we have A that is moving 10 kilometers an hour towards right, and we have B that is moving, let's say, not let's say 30 kilometers an hour towards the left. So we need to find velocity of B with respect to A. So when we are taking A as the frame of reference, what happens is we go and sit in A, and the frame of reference has to be at zero velocity. Now if I want to make this zero velocity, right, it is going at 10 kilometers an hour. How do I stop it? I give it a velocity in its opposite direction, so it is moving towards the right. I give it velocity towards the left. How much? 10 kilometer an hour. Now since I'm moving this with 10 kilometer an hour, I'll have to move this with 10 kilometer an hour too in this direction, right? So what our final situation would look like is basically your A would come to rest while your B over here, while your B would actually be moving with 40 kilometers an hour. Now what this entire scenario means is that if you were sitting in car A, if you were sitting in car A from the initial point itself, then it would seem as if you are at rest, but car B is coming towards you with a velocity of 40 kilometers per hour. Now that is kind of interesting, right? That is why it feels as if when two cars are traveling in opposite directions, it always seems as if the person who's coming towards you is coming at a very very high speed, even though he's just traveling at 60 or 70 kilometers an hour. When your speeds add up, it seems as if he's coming at 200, 300. Okay, 300 is a little too much. 200, 150 kilometers an hour, right? It seems like a lot, but actually the thing is your speeds are actually getting added, right? Your speeds are getting added. Now make sure that when you're adding this 10 kilometer per hour, don't just add it to A, make sure you add it to everything else. By everything else, it means even the ground. So it would seem even the ground is moving towards A at 10 kilometers an hour. So I hope you guys understood everything till this point, and hopefully everything is clear so far. Now what I'm gonna do is I'm gonna take another sip of water. Till then, if you guys did not understand it, you guys can just go back and just repeat this once more. And this only just this section, don't watch the entire thing again. So just watch this section again, and hopefully you guys can understand over there. If you still have any doubts, I have given contacts in the description, so you guys can reach me out over there and I'll make sure that I help you guys. Right now, let me take my sip of water. Also, I'm shooting this at 1 a.m. That isn't PM. What do you see over there? That's not PM. That's AM. um it's all right to be nocturnal. Yeah, I that's what I would say. Now we have one more term that's left, that is acceleration. Right, we have another term. Now this term is pretty easy to actually understand since we have already dealt with the previous terms. Acceleration. What is acceleration? Acceleration is basically the rate of change of velocity with respect to, guess, time. Exactly. So acceleration is basically the rate of change of velocity with respect to time. And also there are multiple types of accelerations. First we have uniform acceleration. Uniform acceleration means that in a given time interval, your velocity is changing at a constant rate. All right, whenever you have a term uniform, it basically means constant. Right, I would actually like to use this. Let me just erase this one. Yes, mouse, come on. Yeah, okay. Yeah, sometimes it lags. Hopefully that's not a big deal. Okay, so uniform basically means constant. And non-uniform, when we talk about non-uniform, that basically means variable. So yeah, then we have something known as instantaneous. Right, we have instantaneous acceleration. Now from the previous, from your previous term encounters, and from the word itself, what do you think instantaneous acceleration means? Right, what do you think instantaneous acceleration means? Instantaneous acceleration is basically the acceleration of a body at any instant. Okay, acceleration at any instant. Now, how do we get instantaneous acceleration? Exact same way as we got instantaneous velocity. What we do is we know that acceleration is the rate of change of a velocity with respect to time. So we can write acceleration A. Okay, we can write acceleration A is equal to delta V by delta T. What this means is that this actually gives you average acceleration. All right, so we can write this as A average. So the complete change in velocity with the total change in time. All right, that gives you average acceleration. Now, what does average acceleration mean? Use the exact same analogy as you used between displacement and velocity and acceleration. Average acceleration is basically the acceleration that would be required to, meet the requirements of this delta V in the same time interval if it were a constant value. So that is what your average acceleration is all about. Now when we talk about instantaneous, so if I write A instantaneous, can you guess what this is? I'm pretty sure you guys already did. So limit delta t not equal to theta, limit delta t equal to 0, delta v by delta t. Okay, so this is what we have. And another way to represent this is also a instantaneous in the differential form is dv by dt. Now we can also write one more thing. So we can write a is equal to dv by dt. I won't keep writing instantaneous. Hopefully from now you guys would be able to figure out when I'm talking about instantaneous acceleration or velocity and when I'm talking about average acceleration and velocity. So mostly we're going to be dealing with instantaneous acceleration and velocity in this chapter. So yeah, and if we want to write it in another way, not this limit way, the other way is the double differentiation. All right, double differentiation of displacement with respect to time gives us acceleration. As I said, there's a basic prerequisite of differentiation. So what this means is, let me just go ahead and tell you. So if you differentiate displacement with respect to time once, right? When we differentiate it once, then this gives us velocity. But when you differentiate, so the first differential of displacement with respect to time gives us velocity, and we know that acceleration is basically the differentiation of velocity with respect to time. So what we do is we differentiate ds by dt with respect to dt again. Do you understand what I did over here? So this is basically, let me just scroll down. So this is basically our d2s upon dt2. All right, and this represents our acceleration, of course instantaneous acceleration, since it is in differential form. So this is all about acceleration and velocity. Now there are three equations of motion. All right, there are three equations of motion. Now we can derive these, but to be honest, it's kind of useless, right? It's really kind of useless. You can use graph to derive this. If you want, I can make a separate session on just that, but to be honest, you really will never need that derivation unless you have that derivation that will be asked, right? And that pretty much is very rare, right? So for this occasion I'm going to be avoiding it, and if you guys really think it's important for you, just leave a comment down below. I'll make a video on it, right? So you just need to remember these three equations of motion, and if you know, if it makes you wonder how you're gonna go ahead and learn these three equations, all you have to do is you just have to use it a couple of times, right? You have to solve questions. When you solve questions, you will be able to remember it by your own. You don't have to just sit and cram. All right, that never works. Whenever you have to remember an equation, or whenever you have to remember a formula, or yeah, basically if you have to remember any expression, equation or formula, you have to use it multiple of times. You have to use it a multiple times, right? And then it just gets stored in your muscle memory as well as your real memory. So now the three equations basically are, let me write it with yellow. So first, it's not in order, there's no specific order for it. So you can write v is equal to u plus at. V square is equal to u square minus 2as. Yes, I will tell you what v, u, a, s, t are. And then we have s is equal to ut plus half at square. Now I'll tell you what each one of these are. So v, u, a, s, t. Okay. Yeah, I'm putting a lot of effort in using different colors so it doesn't look boring for you guys. So v over here is basically the final velocity. U over here is initial velocity. A over here is acceleration. S over here is the displacement. remember it's not distance, it's displacement. And t over here is the time taken. Alright. So now you have everything that is required to, actually solve questions relating to one-dimensional kinematics. Now we'll be solving one question. Alright. We'll be actually proving one thing. And what we have to prove is, let's say we are on top of this apartment. Alright. Let's just say this. This is our apartment. Now what I do is I have a ball in my hand. Alright, so I have a ball in my hand. Now what I do is I throw this ball. Okay, I just throw this ball flat. Alright, there's no projectile, don't get scared. If you don't want to see that, let's say I just leave it. And it directly just falls down. Let's say this is our case 1. Okay, this is our case 1. So in case 1, let the time taken by the ball be equal to t. Alright, then we will move on to case 2. Alright, wait, I'll just specify a few more things. I'll mention that the height of this is h. Alright, so yeah, now we will talk about case 2. Okay, what happens in case 2 is, again, we'll have the same apartment, same building. You go to that building. Give me a second. You go to that. Oh my god, just help me make this. Okay, so yeah. So now you're at the same building. Again, this is also of height h itself because it's the same building. You're standing over here and you have a ball in your hand. But this time what you do is you throw it up with an initial velocity u. Now let's call this our case 2. Now let's say that the time taken in this case over here, the time taken by the ball, everything over here remains the same other than this thing over here, this situation right over here, other than this initial velocity that you're providing in this case. In other case, you're not providing anything. So the time taken over here, let this be t1. Alright, and now we'll move on to the third case. I'm pretty sure you guys figured out what the third case will be. For those of you who didn't, no problem. So what our third case is, that we have the same apartment and this guy is completely jobless. He has nothing better to do in life. Okay, that was hard. That was harsh. It kind of reminds me of me. Okay, no self roasts. Okay, what is happening? Okay. Alright, so now what we do is we give this ball a velocity u downwards, and this becomes our case 3. And let's say the time taken here for the ball to reach the ground, time taken by ball, let that be equal to t2. Now what the theorem states, we'll be proving this theorem, and that will actually help us figure out every single thing at once. Alright, it will allow us to actually master this entire concept of one-dimensional motion at once. Alright, so what we do is what the theorem over here states is that, wait, I'll just go ahead and write the theorem. So theorem is that t is equal to under root t1 times t2. So we have to prove this. Alright, so this is what we have to prove. So let's go ahead and get started. Alright, first let's go ahead and calculate t. What we're going to do is we're going to individually calculate them, and then we'll see whether they equate to each other. That's a way of proving, right? So what we'll do is we will see what t is equal to, then we'll find what t1 into t2 and take the square root of that, what that is equal to. And using that, if the answer is coming the same, then hence the theorem is proved. And what I'm thinking is maybe two-dimensional motion, I'll cover it in another video, because that thing is, of course, it's kind of small itself, but I wanted to do circular motion as well, but I can't just leave circular motion for another episode all by itself. So two-dimensional motion, we'll cover it in another episode, in the upcoming episode. And right now we'll just finish with this last theorem thing and we'll be done for today. All right, so right, let's actually continue. What was I going to say? Yeah, so let's go ahead and find what this t is equal to. All right, let's go ahead and solve what this t is equal to. So we are given that, first let's write what is given to us. So whenever you're solving these kind of questions, what you do is you write given, and we are given what? We're given height. We are given height, and height is equal to what? H. We're given initial velocity, which is equal to 0. And yeah, so now we need to find the time. So let's just write all the three equations of motion. It just takes 2 seconds, and when you have it in front of you, it's just super. V is equal to u plus at. And over here, make sure that you know that this acceleration over here, we switch it and we put it as a is equal to g, and this g is basically acceleration due to gravity. Acceleration due to gravity. Alright, if you want to know more in depth about this, then we'll be doing that in the gravitation chapter and not here. Right, so if we see, I'll just write it in the form of gravity, taking a as g. So we get v is equal to u plus gt. Then we get v square is equal to u square minus 2gh. Alright, putting everything in place, and we get h is equal to ut plus half gt square. Okay, now what we can do is, can we calculate the final velocity? Of course we can. If we go ahead and calculate the final velocity, using this, we get v square is equal to u square minus 2gh. Now this minus is basically not magnitude, it represents direction. So you can actually ignore this when you are taking the square root. So what we are going to do over here is we get v square is equal to 2g, because that thing is equal to 0, right? So okay, it's kind of lagging, but that's all right. So this is equal to 2gh, so we get v is equal to under root 2gh. Cool. Now I would suggest that you guys try this on your own, but if you want to just see it, it's cool. So now we can calculate the time, right? I know we could have just done it from here, but this is a lot simpler. So what we can do over here is v, we know final velocity, which is under root 2gh is equal to initial velocity. Initial velocity is 0 plus gt. So can I write t as under root 2h by g? I can say this, right? So now we have calculated t. Okay, similarly what we're going to do is we're going to go to case 2 and we're going to go ahead and calculate t1. Okay, so let's go ahead and calculate t1. So to calculate t1, we know that initial velocity, we are assuming, okay, so we are assuming that down is positive. Alright, as I said, sign convention is up to you. So down is positive, up is negative. So now what happens is we get v is equal to u plus at. We have v square is equal to u square minus 2as, and we have s is equal to ut plus half gt square. Alright, now can we write v over here, the velocity over here Actually, time over here is kind of simple if you see, but how about I just, use the formula and just, So if I write it as this, we get h is equal to minus u. Why minus u? Because we're taking uh, upward direction as negative and we're taking downward direction as positive. Alright? Sign convention basically. Into time plus half into g times t square. Now we can see that this is a quadratic equation and we're just going to use the quadratic formula and solve this. So we get gt square by 2 minus ut minus h equal to 0. Now what I'm going to do is go ahead and make the coefficient of t square as 1. So for that I have to multiply everywhere by 2 by g. Right. So it will be t square minus 2u by g minus 2h by g. Alright. Now what I'm going to do is use the quadratic formula. So on using the quadratic formula, we get minus b, which is 2u by g. Of course, I forgot to put t over here. Minus b, not plus, that's not plus, that's a t. So minus b, let's use this, plus minus under root b square. B square is going to be what? 4u square by g square minus 4. We can write plus minus 4 times minus 2h by g. Alright, divided by, the entire thing should be divided by what? Entire thing should be divided by 2a. 2a, that's basically 2. So this is going to be one of our equations, and if we simplify this a little more, we get what? 2u by g plus minus under root 4u square by g square plus 8h by g. Entire thing divided by 2. Okay, actually, if I simplify it even more, then we get something like this. U by g. Oh my god, what just happened? Give me a second. So if I simplify this even more, then we get u by g plus minus, if 2 comes out, so if we took 4 common over here, so it will become u square by g square plus 2h by g. Alright, this is what we get on simplifying. So this is t. Alright, this is what t is equal to. T1 is equal to. Now we go ahead and calculate t2. Alright, now where is t2? T2. Alright, this is where we calculate t2. So what we are going to do is we'll directly just hop on, and we can write h is equal to, we're taking down as positive. So we can write h is equal to ut plus half gt square. Alright, so it's going to be ut plus half gt square. So what I'm going to do is ut plus half gt square minus 4, what am I doing? Minus h equal to 0, right? So now we have our quadratic again. So we're going to go ahead and use the quadratic formula once more. And on using the quadratic formula, before we use the quadratic formula, we should go ahead and simplify. So first let me just write it, gt square by 2 plus ut minus h equal to 0. And then we can write that now we're going to go ahead and divide by g by 2, or basically just multiply every single term by 2 by g. Alright, multiplying by 2 by g is the same thing as dividing by g by 2. Alright, hopefully you guys know that. So Now what happens is we get t square plus 2u t by g minus 2h by g equal to 0. Now when we put this in the quadratic formula, we get t2, right? This is t2. So t2 becomes equal to minus b plus minus under root b square is what? 4u square by g square plus minus 4 into minus 2h. Now I'm pretty sure you guys would notice something over here divided by 2. Right, I'm pretty sure you guys noticed something here. Now if you take 4 common again, you're going to get minus u by g plus minus under root, you can write u square by g square, and over here you'll again have plus h by plus 2h by g. Alright, so this is your t2, and where's your t1? Let's see, and this is your t1. So if we go ahead and multiply t1 and t2, so your u by g plus under root u square by g square plus 2h by g into minus u by g plus under root u square by g square plus 2h by g. What is this? What is this term over here? This is basically t1 into t2, right? This entire thing, this box that I made over here, that is t1 into t2. So this thing over here is t1 into t2. So now we're just going to go ahead and multiply. So on multiplying, what do we get? On multiplying, we're going to get, this is basically a plus b into a minus b, which is going to be a square minus b square. So it will be u square by g square plus 2h by g minus u square by g square. These two will cancel out. Now if you take under root t1 into t2, that will be equal to, give me a second, so that will be equal to under root t1 into t2 is equal to under root 2h by g. Now if we go ahead and look at what the value of our t over here was, what was the value of t? If this computer doesn't lag, yeah, so over here we can see that the value of t is under root 2h by g. So we have proved the theorem that this time over here is equal to the square root of the product of the other two time intervals, right? And that will finish our session for today. Now hopefully you guys enjoyed the session, and if you guys did, make sure you guys share it with your friends who are interested in physics and who actually want to learn it in greater depth, right? And I'll also have a practice session on kinematics, but that will be after we're done with Newton's laws of motion and work by energy, so I can combine all of them and actually give you the real questions of physics, because solving questions individually from kinematics isn't really going to help you that much, but when you interlink concepts and then you solve it, it gives you a whole different pleasure, right? So this will be the end of today's session. I will see you guys in another video. Till then, goodbye.